Here we have a particle that has a mass of 7.8 kilograms. It's traveling in the xy plane with a given velocity. We want to find the angular momentum about the origin, the instant that it's located at some given position. So we'll start by giving ourselves a coordinate system so that we can identify where the object is, how it's moving, etc. Now we'll find the position of the object. This is negative 4.6 in the i-hat direction, so this is negative 4.6 to the left. We can denote that component about there, and then we are negative 6.3 in the j-hat direction. That's negative 6.3 in the y direction, or 6.3 downwards. And so we have these components, and that gives us an overall position vector that looks something like that. And that is indicating the location where the particle is at this instant. We're told then that the particle is moving with some velocity. Its velocity is negative 1.9 in the i-hat direction. That's the x direction. So negative x direction would be the left, and 9.4 in the j direction. That is up. And what we're going to do also, since we are trying to find the angular momentum, is we're going to say that the angular momentum is r cross p, where p is the linear momentum, and that is mass times velocity. So we're going to end up taking the cross product of these vectors. That's what this is saying here, but we're not taking the cross product of v, we're taking the cross product of p. So we'll go ahead and find the angular momentum first. The angular momentum is the mass, which is a scalar, just a number, and that is going to be multiplied by the velocity vector. We can distribute this just like we would anything else that's being multiplied, and we'll find the linear momentum vector to be, linear momentum vector to be thus. These units here should be units of kilogram meters per second. That's the units of momentum. It doesn't really matter how big we draw it on the graph. This is a graph that's measuring position. It's not measuring momentum, so we just need to draw this proportionally. We can notice here this is about 5 times as big as that, and so when we draw it, we should draw the y component about 5 times larger than the x component. And here we have the momentum vector. If we want to actually find the angular momentum that is associated with this linear momentum, the angular momentum about the origin, then we'll take the cross product of r, the position, as measured from the origin, and the the linear momentum. So this equation here, we're going to have r crossed with p, the linear momentum. Now this is a cross product, so we will distribute these terms, and we will take the cross product of each one. Here I have distributed out all of these terms. I have 4 terms for the 4 different multiplications that I'll have. In each case, I'm multiplying the coefficients, and then the cross product is going to be between the unit vectors. A couple things to remember. Here I've distributed out this cross product. I have 4 terms corresponding to the 4 different permutations of terms that we have. In each case, I multiplied the coefficients, and then I distributed the cross product I cross I, for example, here. Remember what we said about cross products. If you cross I, that's the same vector. Those are always parallel, and so the cross product there is going to be 0. The same thing, j cross j is also going to give us 0. I sketched this little diagram out to remind myself. I cross j is k. So this should be in the k-hat direction. That shouldn't be a surprise. If everything here is going in the xy plane, then we would expect to have angular momentum perpendicular to that plane, which should be pointing in the k-hat direction or in the z direction. If I cross j is k, then going backwards, j cross I would be negative k, would be pointing in the negative z direction. So I have two surviving terms here, and I'm going to actually multiply these out and combine them to find the overall angular momentum. Here I have my overall angular momentum. If I look at sig figs, I see that I have two sig figs, so we'll go ahead and round this to negative 430 kilogram meters squared per second, and this is in the k-hat direction. What that means is that this is going to be clockwise, right? The k-hat direction is the z-axis. When we say we have positive rotation, that means that we are rotating counterclockwise and in the xy plane, and our vectors in the z-hat direction. Here, this vector is in the negative z direction, so the negative k-hat direction, and so that means we would have clockwise rotation. And in fact, you can see here the momentum moving in this direction has a tendency to rotate clockwise around the origin if there were going to be rotation in that case. If we wanted to find the angular momentum about a different point, we could do that, right? If we were looking at the point 0, 2, and this were going to be our axis of rotation, we would have a new, like an r prime, a new position, and we would have the same momentum would give us a different angular momentum about a different location. So angular momentum, like other angular variables, depends on the momentum of the object, but it also depends on the axis of rotation, or you could think of it as the axis of potential rotation, whether the object could potentially rotate about the origin or whether it could potentially rotate about a different axis of rotation. You'd have a different angular momentum associated with that.